term frequency or TF-IDF, you know, to build like inverted index using terms, and then have posting lists. Sometimes the posting list can be very big, like billions, that can not be that good to manipulate. So we wish to use vector space modeling because with vectors, we can have like more flexibilities. We can use notion from linear algebra, for example, to reduce the dimension of very big vectors. Or when we have a sparse metric, we can easily reduce the dimension. And also we can use it to better represent like the situation that we have. So if we have two vectors, we can easily compare them and see what's the similarity between them. So if we can represent, for instance, a query as a vector, and we can present a document as a vector, we can measure the similarity between these two vectors. So this is what you did in your homework assignment, like the experiment we did. So today we will see mainly particular topics where we have a data set of items. What we want to do, we want to recommend some items to a user based on other items that we know the user likes. So for example, if you do not want, you don't have a particular type of fish, but using the data set that we have that describes what is the composition of the fish that you have, okay, we can then compute the similarity between the fish that you provided that you don't know, we do not have, to find like similar that can compensate with the number of, I don't know, number of vitamins that it has, the number of the calories, and so on. So basically, we are going to build a recommended systems based on similarity-based recommended systems. So for that, we are given this data set. So we are given this data set, which basically contains like food with the nutritions that the food, each food item has. So we use pandas to read the data set. You should be familiar with this library. Read data set, extract the features that we need, and also the class label. So this is what the first cells will do. And it performs some printing. So you will print like the names. We have different names of foods. We have different classes. Here we have basically 3 classes, whether it's seafood or fruit or saving foods. And also we have several dimensions, which are the features, also called the predictors. So when you take a look at these tables, we can see that you have several features like calories, total fat 1. So these are protein, vitamin A, vitamin C, and so on and so forth. So if you have 2 particular items that are having similar properties, okay, so this means most likely they can provide the user may prefer the same item because it is similar to others items. However, we can see that if we check the dimensionality, for example, we can first assign different colors to different items just for plotting to distinguish them, each other. And then we can do some plotting. So this function is useful for you. You should be familiar again with this library, matplotlib, and then for plotting. So this function I given to you, and then we use this function for data visualization. So if you are given like a matrix, we can visualize the matrix as an image to see, for example, if there's correlation between features, okay? And then based on this study, we can, for instance, randomly pick two features and plot them, okay? To see how the data distribution looks like. So if you took a look here, we have plotted potassium 1 versus calories fat from fat, okay? So here we can have a look at the distributions, just 2 dimensions. But here we are having more than 22. We have exactly 22 dimensions, okay? So we may want to pay attention to the most relevant dimensions, the most useful one, the most informative dimensions, okay? So the 2 that we choose, we are not sure that these are the most relative, the most informative dimension. So when we randomly choose a calorie fat and then potassium 1. So this is random, okay? So one thing that we can do to say, okay, we want to reduce the dimensions is that we can have, we can plot the correlation matrix, and just if we have 2 features that are very highly correlated, we drop 1, okay? Because they give us the same information from the data set. And however, we can have a bunch of data. There are techniques that we can use to reduce the dimension of this data. And after reducing the dimension, we can then apply any technique that we can use to compute the similarity between them, okay? And with very high performance because the dimensions are, of course, low. So the task today is to use principal component analysis to reduce the dimensionality of the data set that we have. So you have it from PCA, from scikit-learn, the composition package. So we can apply PCA, but specifying the number of components that we want to extract from the data set. Okay. So again, you should be familiar with the notion of principal component analysis and how does it works and how is it useful in our case. So in this series, what we expect to do is just apply PCA to extract the 3 principal components. The value K is 3. Okay. So what we want to do is to say that we want to extract components that are most informative from our data set, or the component that contain the most variance of our data set. Okay, so if there are components that are less informative, we can just drop them. So we extract the top K1. Okay, so you can fill this set and apply PCA to reduce the dimensions. Meanwhile, I will maybe. So we are in vector space model lab. You can have it in the GitHub repository. So we can recall what are the steps to, if you want to apply PCA from crash. What are the steps for PCA?
We need to calculate the correlation matrix, then normalize it, but to make it subtract the mean. Then we will have the SVD, apply SVD, take the top top 10, or like the top number of K dimensions, and then apply this to the data.
Yeah, that's the idea. But first, we need to center the data around 0. Okay. After centering the data, we compute the covariance matrix. Okay. We change examples, and then from the covariance matrix, what you do, you compute the eigenvectors and eigenvalues of the covariance matrix. Okay. And the eigenvalues tells you which eigenvectors are most informative. Okay, so the highest eigenvalues are the highest the vector associated is informative from our data set. Okay, and then we can extract the top 2, the top 3, the top 4 one, depending on how many components you wish to have. Okay, so what criteria can guide us to select the number of components?
Explain variance.
Yes, we can use explained variables, or the amount of variance that is returned by those components. Okay, because each value, each eigenvalues tells you how many variance is maintained by this particular eigenvector. Okay, so you can then sum up each eigenvector and divide by the total number of eigenvectors that you have until you reach the threshold of the maintained variance that you wish to have. I hope this makes sense for everybody.
One question I have.
Yes.
In PCA, we have principal components, right? And each principal component is some linear combination of the original features. Right?
Come again?
the principal components we extracted
Yes.
for PCA. Each
Yes.
of them is a linear combination of the original features there.
Each of them. And from this, you can see which projection will like give the lowest projection error, right? Which is also associated to the amount of variance that you have in the projection, right? So we see that, okay, this component is the one that preserves the most variance, okay? And what tells us this one? It's like this is an eigenvector, this is another eigenvector, okay? Now they are associated with eigenvalues. The eigenvalues tells us how much variance is maintained by this component. So you have the eigenvalue lambda1, have the eigenvalue lambda2. For this projection, lambda1 will be greater than lambda2. Okay, because lambda v1 has more variance than v2. Okay, and how do we compute this eigenvector? You know the formula from the to have the eigenvector. It's like if you have v and lambda. If v is eigenvector associated with value lambda, this means for the matrix A, if you multiply A by V, it will just scale V by a certain factor. So you have this formula, right? So if E, V is the like eigenvector. And then from there, you can find easily, first you find the eigenvalues, and for each eigenvalues, you find the corresponding eigenvector, okay? And then you solve those eigenvectors by orders of eigenvalues, okay? And then you should pick up the K1 and then you project. So this means that you will pick the top K. You have the top K lambda K, okay? So let me write it differently. So you have lambda1 into lambda 2. So now this is when K is given. You're saying that one K is equal to 2, okay, K is equal to 2. But sometimes you do not want just to pick a random value of K. You want your data to be as informative as possible. So how are you going to pick K? You can look the amount of variance that you return when you project your data into those K spaces. Okay? And this lambda tells you can compute this ratio of variance return. So if you want to compute the ratio of variance return, you can sum, let's say G from 1 to K of those lambda K. Okay? And you divide it by the sum of I from 1 of all the lambdas that you have. So lambda 1 tells you how many variances returned by the component associated to lambda 1. Lambda 2 tells you lambda 3, and so on and so forth. Okay? So if you want this to maintain at least 90% of the variance in the data set. So from this equation, we can try to find the value of K that satisfies this. Does that make sense? Yeah. So this is how we can get you to decide which value of K that you choose that will maintain 90% of the values. Because if you choose a value of K that you have just 50%, you're losing a lot of information when you do the projection. Okay? This can mainly occur when, just imagine that you have a data set that is very uncorrelated. So let's say you have a data set like this. So let's say you have this data set where your points are distributed like this. Okay? Is this data set correlated? They are not correlated, right? So even no matter the direction that we choose, so regardless which direction you will choose, okay, the value of lambda 1 and lambda 2 will be slightly close to each other. Okay? And if you want to maintain 90% of the variance, you should keep all the components. Because if you keep just one component, just one lambda, you will lose almost 0.5% of the variance in the data set. Okay? So this also depends on how correlated the data set are. But it can be not correlated with these two dimensions, but with other dimensions, they are correlated. Okay? So we want to look at that dimension where the data, the variance vary the most. Okay, and present them. So, but when you sum all these lambdas, it tells you like the total amount of variance. Okay, so amount total amount of variance, if I take k lambdas, how many variance do I return from the projection? Huh? What? Where's DK? It's not D, it's lambda. It's lambda K. So this lambda K. Yeah. So you just the ratio of variance that is required. So this is how you can get you. But in this case, for instance, the projection can be very bad and then you lose a lot of information. So generally what you want to do is that you have a bunch of dimensions. Some dimension can be correlated. And you know that in ML, if you train a model with highly correlated features, they can be hard to optimize. Okay. So when you apply PCA, you will drop those correlated dimension and just keep the most informative one. There are even dimensions that are useless, not telling anything about data, you can also drop. And then this will give you this value of lambda that is very close to zero, not big enough. Okay. So here we want to apply PCA to reduce the dimensionality, and we want to keep three components, right? So you are familiar with PCA. You have access to this notebook. Okay. So what should we write here to apply PCA? Is vector space model. Funny. So in that first case, apply PCA to transform the input data. So basically, the PCA, we will go with you have the PCA instance, and we have PCA.fit transform, right? So we have fit transform. Again, as we said, the step of PCA, from what we saw before. So from what we saw before, we saw that this will apply all the steps for PCA for us. As we saw, the first step is to center the data around zero. Okay, so we assume like a normal distribution. So we subtract the mean. Okay, so you have your matrix. The next step is to compute the covariance matrix. So you have the covariance matrix of all the rows that are in N. Okay. Yeah, so you have the covariant values of S, for example, okay? And then you compute the eigenvalues and vector of S, okay? So then you have to solve, next step, you have to solve the eigenvalues by eigenvectors. Eigenvectors by eigenvalues. Because the highest eigenvalues tells us which is the most important component, okay? In the last step, we project A to the top K vectors. Those are the steps. So we saw this in reverse order, okay? This is in reverse order, and then we project. So after the projection, we can then analyze what is the percentage of variance that we return, right? So to analyze that, so this fit transform will do this for us. And then we need to run the previous cells. And then I need to do it fast. What is the error? Oh, this is true. So after transformation, you can see that my new APCA is of dimension 61, 3. So we have kept the top 3 dimensions that are most informative of my data. And then we want to compute the explained variance ratio, right? How many variances return? How many information do I keep when I use only those 3 components, right? So from PCA, if you recall, or if you check documentation, so from PCA, you can call the PCA dot explain. So you have to explain variance ratio. This will give you an array of k values. Each values correspond to the amount of variance that each component maintain. Okay. And to have the total amount of variance, you have to sum out of them, as we saw before, right? So if you take the sum of the sum, you basically have the total amount of variance that we maintain when we use those 3 components. You can do that. You can print this. Yeah, you have the top 3 values. This is the amount of variance that you maintain from the first component, the second component, the third component. Okay, so the total amount of variance that you retain by using the 3 components is the sum. Okay, so when I take the sum, you can see that, okay, we maintain 90% of variance. So those 3 components are very informative. But if I skip one component and I use only the first component, I will keep just 56%. This means I'm losing a lot of information from the data. Okay, so we reduce the dimensionality, and then we can then plot on our data set on these dimensions. Okay, so if you want to plot in 2D, 2 dimension, we use the first component. Okay, if you want in 3D, we plot the 3 top principal components. Okay, so when you plot, you can see that, okay, red points are close to each other, blue points are also close to each other, but just they're entangled with green points. Okay, so we went from 22 dimensionality, we use PCA to reduce dimensionality, and we have an idea. And we can see that in green points, red points, they are mainly fruit, right? And then you have like, green point fruit, you have seafood in red, okay, and you have vegetable in blue. So you can see that fruit and vegetable are close to each other because they contain, they have the same like nutriment, okay? So this is done with PCA. Another way of performing the dimensionality reduction is SVD, which is singular value decomposition. It gives us very interesting property that we can use for any type of matrix. Because if you want to apply PCA, there are some requirements that the matrix will satisfy. Like you have to be able to compute the determinant and other things, okay? But with SVD, it's apply another technique where it decompose a given matrix into 3 different matrices, okay? And from these matrices, you directly have this information about what are the principal components and what are the associated values, eigenvalues. Does that make sense? And then you can just compute as the matrix multiplication of those components and the values that you have. So let's have a small visual. What is the difference between what? Yeah, sure. So what is interesting with SVD, so you have singular value decomposition. So for any matrix A, it says that you can rewrite it as 3 matrices. So you have matrix V, have sigma, and you have V transpose. You can decompose it in 3 elements. These are singular, you have the right singular vector, the left singular vector, and then you have the singular values in the middle, with sigma, okay? So here you have a matrix where each column is represented by a particular vector, okay? Then you have this until UN. You have V. So you have sigma. What is sigma? Sigma is a kind of matrix. What kind of matrix? Yes, diagonal matrix. So you have sigma where you have lambda 1, lambda 2, lambda 3 until lambda L, okay? But everything else is 0, okay? Because after lambda L is the rank of the matrix A, okay? And then you have next, you have the transpose of V. So you have V1 transpose, you have V2 transpose, you have Vn transpose. So also this matrix is a rectangular matrix, okay? So U and V are squared matrix, okay? And what does it tell us? What is interesting is that if you can decompose the matrix in these 3 factors, satisfy these properties, this lambda 1 is greater than lambda 2, it's greater than lambda 3, and so on, until lambda L, okay? Greater or equal. Yeah, and also, this tells us that the first component here is the most informative from the data set that you have. And then you have the next one. So you can rewrite A as, you can write it as lambda 1, U1, V1 transpose, plus lambda 2, U1, U2, V2 transpose, and so on. Okay, this tells us this one is the most important. So if you can rewrite A like this is a good approximation of A. So this product is like the best approximation of A. And this implicitly tells us like these are the principal components that you can use. So you can consider either this one, the next one, or the K1 that you want to consider. Okay, but this at a certain time it will become just 0 after lambda L. Okay, because it cannot be more than the rank of the matrix. We cannot find those orthogonal components that are more than the rank of the matrix. And then having that, you have the principal component basically. You have the most important part of your data. And of course, the estimate behind it, you see this is somehow close to what PCA does. Okay, so for instance, you will see that if you compute A transpose, okay, this will basically have U will be the eigenvectors of this matrix. That makes sense? And if you have A transpose A, we have like eigenvectors will be V as eigenvectors. Okay, and those two matrices will share the same eigenvalues that are here. Do you understand the intuition? Remember, A transpose can be seen as what? When you want to compute the covariance matrix, you take A transpose, you divide by A minus 1. This is a covariance matrix. Okay? And if you decompose the covariance matrix with SVD, directly what you have the eigenvectors U that you need for PCA. Okay? And you have all the eigenvalues associated with which are sigmas. Okay? So that's the intuition behind SVD and how it works. Of course, you will see that since U and V are orthogonal vectors, you have U transpose, which are equal to the identity matrix, V transpose equal to the identity matrix. This is how you can derive that this one is the eigenvector of U is the eigenvector of A transpose. Okay, because if you compute A transpose, it's equal to what? You have A here. Let's take a look. So if you compute A transpose, what is A transpose? If you want to compute the transpose of this, which is A sigma V transpose, if you transpose everything here, okay, you just reverse and add transpose where it's needed, right? So you will have something like V sigma U transpose, right? So when you compute A transpose, you have A transpose is equal to what? You take the A that you had before, which is U sigma V, yeah, V transpose, and have V sigma U transpose. Okay, so since these are orthogonal matrices, they sum up to identity matrix. So you have this equal to U sigma squared, okay, U transpose. Okay, so you can use this to find those U that you want. Okay, the matrix, and also know that, and you end up saying that, okay, if you, for instance, we compose this by V, so if you add V here, I mean, if you add V to the left, no, if you add U to the left and U to the right, basically what will you get? If you add here, if you add A transpose U, and then you add U here, right? This will be what? Identity matrix. And then finally, what you get that U A transpose U is equal to sigma squared is equal to U sigma squared. Okay, so basically this tells us that U is the eigenvector of A transpose, and you find the eigenvalues associated with sigma squared. Does that make sense? So if you recall the eigenvector, if it is eigenvector, this means that you have EV is equal to lambda. Okay, so here is A transpose. So this is how it's related. So when you have the singular value decomposition, you have those transformations that you can perform. And then you can just use this transformation to keep the top K values that you want. Okay? And then you have the kind of projection of the data that you have. Okay? Well, so, and then that's what we're going to apply in the next task. So in next class, we're going to do the same thing, but using SVD. Okay, we can use SVD from NumPy linear algebra. Okay, so you apply SVD and it will compute those three matrices for you, like this transformation of matrices for you. Yes, and then in U underscore, you just get the top K1. Since you know that they are already ordered by a number of eigenvalues, okay, you can extract the top K1. Okay, and then you can just, to have the new transformation, you can just multiply matrix multiplication of U and sigma. Yeah, and this, yes, and this S square is like you extract the auto diagonal matrix. Yeah, so it's how the diagonal matrix from sigma. Okay, so very straightforward. You can apply here. You can go ahead and test for yourself. You can have similar decomposition of A. Okay, once you got it, you can then extract the top K component of it. So you keep all the rows, but you want the top K columns, right? So you keep the top K columns. And for S, we can use np dot diagonal. So we can extract the diagonal of sigma. So for sigma, you get the top K sigmas. Okay. And then you can do the same for V, but we are not going to use V. For V, you can check, like, you can use V transpose and also get the top K1, or you can just not transpose but get the first rows. Okay. And for AVD, we just use the matrix multiplication. We have mat mole of new sigma. Okay. And that's it. Here we want the top Q. So the top Q. And this is S before we. Okay. So here we have to extract also the same dimension. So we get here the first. We get the first K rows. And the first K columns. So this is where, this is here. So here, when we say we put two columns, we take all the rows, right? If you want the first K columns. Yeah, anything and then stop at K. And then the same here, anything and then stop at K. What about the second row with sigma? So we extract the diagonal matrix. Seems like no.
Is DNT. Should be as well. Okay.
Ah, yes, sure, it's okay, but that's not the issue. The issue is here. So let's see the let's check the shape of sigma. Right, sigma dot shape. Okay, 22, and then we want to get the first K1. So we get the first K1 diagonal. So let's bring the shape of this one. Yes, looks fine. That's fine. So with sigma is this is the diagonal matrix, which we should multiply by u. So if you have already taken this one, we do not need to get here, for instance. And then there should be S mu. Okay, right. So basically here, either I do like this, or I can extract the top here later on. So after the multiplication, you see that we have our data with 3 dimensions. Okay. Yeah, we don't need V here. Yeah. So next we can plot them using SVD. Now, what is different between SVD and PCA in this case? When you apply PCA, not sometimes, like it needs to center the data first, center around 0, have it like in a Gaussian or normal distribution. Okay, in PCA. Okay, but just when you project your data, you center your data, and then you project into the eigenvector space, you will have like, if there are points that in the original space were like kind of similar, okay, they will lose their similarity. They'll be less similar, less close to each other. Okay, but SVD will not do that. Okay, since it does not center around 0 before performing. Okay, it will keep the similarity between items. So let's take a look here. We can see that after projecting, the red item got entangled here, but they keep the kind of similarity, even the green one. But if you compare with what we get here with PCA, so if you compare what we get with PCA, it's like if you have 2 points that were similar in terms of angle between them. What is the angle between them? Okay, PCA can enlarge this angle. Okay, but SVD, we kind of keep this angle like close to each other. So we'll see next when we compute the similarities between product item to apply that.
For the bug, but the colors are inverted in PCA, like the C code is C code and foods are inverted. Yeah.
And the colors are inverted.
Yeah, but yours is right because it's similar to for example, is SVD. But on the here SVD and PCA are inverted.
We can check it later to see if there's something that you overlooked. So once we have these small vectors, what we can do next is that we can compute like the similarity. If I'm given a query or one item, okay, I need to compute the cosine similarity between this item and all other items. Okay, so if you follow this link, you can have like a quick recall about like the cosine similarity. Okay. So basically, when you can see that you have the norm of the vector, that we multiply by the horizon here, right? So we can apply exactly the same formula that we have. Okay. So in norm vector here, we will compute the norm of each row. Each row represents like an item. Okay. So we compute the norm of each row. Because it's basically the value divided by the norm of that value for each row. So we replace each row by the value divided by the norm of that value. Okay, that's what we do here, norm vector. Okay, so even with the norm vector, we can then plot the norm vector with PCA and also plot the norm vector with SVD. Okay, so this norm vector will then help us later. So first write the code here, computing the norm vector of A, row wise. So vector wise means like you have rows. You use the rows to compute the norm vector rows. So go ahead.
Should we consider the dimensions of A? Here is 63.
What should we consider then?
Dimension of A is 63.
You can extract the dimension of A from A.
No, I mean, here is sample not deducted yet. It's still full text.
You mean which the parameter A?
Then calculate the norm vector.
The norm vector, you need to compute the norm for each rows. So you look for each rows, okay? You replace like you compute this as the value divided by the norm of that row. Basically, you divide the value that is there by the norm of the entire row. So you look through each row. So for each index in the range of, if you want to get the rows, you can get the shape of A, you get the first value. Okay. And basically, we replace the row that we have. Replace it by dividing it with the norm of the vector. So we can use NP dot lean. Let me just record very fast. Lean algebra. Dot norm. So replace it by the norm of that particular line. And that's pretty much it, right? So now we can compute the norm of A. So you have norm vectors of APCA, okay? So you can see how the data looks like when we replace them by the norm, okay? So the norm is useful to compute the cosine similarity. So we do the same with norm vectors. With SVD, we can do that. You can see that they are not exactly the same distribution. They won't look the same, okay? So this will definitely affect the final similarity, cosine similarity score. So now comes the recommendations. You are given a query and a data set, okay? Those are already in norm vectors, already. Okay, and you want to compute what? Find the k closest items to the item given in the query. Okay, since they're already norm vectors, how can you compute the cosine similarity? If they're already norm vectors. So if the parameters here are already norms, okay, how can you compute the cosine similarity? I mean, if in each rows you have like, or in each cell you have the norm of each cell. You can check out like from the formula. Yes. Exactly. Yeah, so you just multiply the query and the data set, the matrix multiplication. Okay. And after multiplying, what we get a value. Okay, which is the similarity score. We can then solve them and pick the top k similar items. Does that make sense? Does that make sense for you? Yes, makes. So we can just apply math np.math narrow. We take the data set, multiply by data set and the query. Okay. However, we want to return only the top k1, right? So we can solve them. We can solve them and have the indexes of the sorted item. So we can use np.argsort, okay? And then we pick the top case. So this will sort in increasing order. Okay.
So we should take the last one.
Yeah, we take the last case. So we get the last case, right? Yeah, and then we can play with it. So we are given 1910, and we want to, let me just maybe create a folder. Create this folder. Oh no, this is not the folder. Create this folder. And then share, I will put it as test. So now we extract the top key, similar item, we're given item that you want to recombine. So return this. So basically, you can see that the most similar item that we have is what? Is pollock, lobsters, and so on. So it has the highest similarity score, or the top that we have. Okay. We have also watermelon and so on and so forth. You can use the absolute value if you want. And let's do the same with SVD. Run it with SVD and tell me how you can interpret the result and why. The norm vector you have add sort, math multiplication, and then you get the last K1. That's should be the last K1. The second question. Which question?
7.
The norm vector, right? Let's see. So what do you get? How to, let me run this again. Yeah, right. So you have the most similar. So we recommend based on the SVD, dimensionality reduction. And then what do you see? And how are the similarities scored?
Orange. 0.2.
What about swordfish? What is the similarity score of swordfish? Or you don't have swordfish? Make sure that you have sorted the closest point. Okay, make sure here you pick the top K one. Should be minus K before 2 parts. So they are one. You can see that here the similarity looks like is higher than with PCA. Okay. Yes. So PCA somehow just account for the variance in the data. Okay. And does not account for the similarity also between points. So in SVD, that's why when you are building a recommender system, sometimes you will want to reduce the dimension based and want to recommend based on the similarity of items. We can prefer to use SVD for dimensionality reduction because you also preserve the notion. Because in PCA, when you project a point, it can happen that after the projection, in a second. So it can happen that in PCA, after reducing the dimensions. So if you have, for instance, let's say you have something like this, and you have data points somewhere around here, right? In PCA, you will subtract the mean. Okay. So if you want to see like if these two items are close to each other, these two items are close to each other, okay, in the same dimension before PCA, when you project, they can become a bit distant from each other. So if you project them in kind of one dimension, so they can look like the similarity. So PCA does not account for that, but SVG does. Okay, so in the original space, similar in terms of cosine similarity items will be also similar in terms of cosine similarity in the reduced space. Okay, because of this projection. So yeah, so that's the idea. So basically what we did is that now someone can look for swordfish. There's no swordfish in your, let's say in your store. You can shop and provide the similar items. Okay, this similarity is what we call a content-based recommender system. Okay, but how is it different from other type of recommender system? What is the limitation of this recommender system? You had a course on recommendation system yet? Do you have a class? Did you have a class on recommendation system? Recommendation system. No, I'm not on this course. Any other course in advanced machine learning, we don't have it out. So basically, the issue is this one is that you see that for each particular item, We know the composition. If you take a look at the data that we have here, we know the composition. By what I mean by composition, we know the number of calories, sodium, potassium, and so on and so forth, right? But just think about the movie. If you want to recommend movie, can you have this detailed description of a movie?
Not exactly, but you can have some links or creative actors.
Yes, but it does not tell you like all the characteristics of a movie itself, right?
Yeah, of course.
Yeah, so you have like user-based recommendation systems. I watch these movies, I start the movies, other users watch other movies and start those movies. Okay, when we combine them together in a table, where we have my ratings and the item that I didn't view or I didn't rate. And have for other users, the item that they view and they rate it, okay? And then you have like this matrix, and then you can resolve it to find what score I may, what score I may give if I watch this movie. Like we use other users' feedback and my feedback, supervise them, collapse them, and then see what's the similarity, and then try to propose the movies that we have like the high scores. What's called basically matrix factorization, which is not content-based recommendation system. It just shows what they use, other users have views. And also we can look like similar users may like similar movies or similar music. Okay, so we can also have similarity between users. Okay, and we can have similarity between items to perform recommendations. I think there is one lecture dedicated to recommendation system in this course, so we will discuss that. So that's pretty much it for this lab. So if you have any question, feel free to just ask. I see there's one online student, Karina. Do you have any question? Okay. So let me stop the recording.